that run it, that we see segments that are inside of triangles. When you guys dealt with, actually I should rephrase this. You guys have all dealt with what's called a median before. You probably just didn't know about it. When you guys dealt with numbers like 1, 2, 4, 9, 10, 15, 21. If I wanted to find the average of those numbers, what would I do? Right. We called that, the average was a name, but what was the other name we called that? Remember that? No, we called it the mean. Remember that? Average and mean were the same thing. But then you talk about what was the median. Remember what the median did? The what one? The middle number. So a median you guys would have done before, well, you just count backwards. The 9. The 9 would be the number in the middle. It has the same amount on one side, the same amount on the other. You okay with that? Now think about that in terms of a segment. Where would a median of a segment be located at? In the middle, the midpoint. You okay with that? Now, in order for us to create what's called a median is going to be a segment that's drawn in a triangle that connects a vertex to the midpoint opposite it. It's different than midsegment. Midsegments, remember, midsegments connected what? Midsegments connected midpoints. Midsegments connected midpoints. Medians connect from vertex to midpoint. Vertex to midpoint is a median in a triangle. The median of a triangle is a segment from, can't write, vertex to midpoint. Excuse me, the median of a triangle is the segment that's drawn from a vertex to a midpoint across. Obviously, it's not going to be drawn to a midpoint next to it because that's already part of the segment. Does that make sense? So if I was going to go from the vertex to the midpoint here, that's just part of the segment. It doesn't help us. But the median is going to be when you're at a vertex to the midpoint. Can I use the word opposite? You guys be okay with that? The vertex to the midpoint opposite. Okay. Now, excuse me. In a triangle, how many medians can you have? 3. Because how many angles are there? 3. How many midpoints would there be? 3. It's kind of convenient how that works. So when you have midpoints, now, one of the things you'll notice that's different when you're drawing here are the medians necessarily perpendicular to the sides? Could they be? They could be, absolutely, they could be, but are they necessarily going to be? No. Whereas if you look at what we had before, perpendicular bisectors, angle bisectors, there was always some segment that was perpendicular to the sides. Medians, how you'll be able to recognize them is that the only thing that's marked up are the sides. Does that make sense? You're only going to see marked up on the side lengths there. Now, one of the things that happens with medians is that the three medians in any triangle, they're always congruent to each other. Okay? The three medians are always congruent. Excuse me. And then they will have a fancy word here in a second. Just want to make sure you guys are okay so far. Do you also agree that they have what's called a point of concurrency? The place where all three of them run into each other? Now, can you decipher that there's two different segments from that median? There's vertex to the point, and then a point to side. You see that? How that segment's made up of two parts? You start at the vertex, you go to that point, you go to that point to the side. Vertex to point, point to side, vertex to point, point to side. Everybody okay with that? The median is made up of two parts. Remember how we can take segments and break them into small pieces? They still have the whole segment. I'm just kind of prepping you for a little something. You get this thing that's called a centroid. The centroid is where three medians intersect. It's actually pretty dry. The centroid is where the three medians intersect. And what we get out of this, excuse me, is a little weirdness. It's called the centroid. So the median, the whole thing, is made up of, I'm going to use segment addition. 1/3, oh, sorry, rephrase this. 2/3 of the median is vertex to point, or I would say vertex to centroid. This sounds weird, but if you want to throw a number in it, it's super fast. 1/3 the median is the centroid side. What's 2/3 plus 1/3? 1 whole. Very good. All right. It just looks really weird with this. So if you start to think about it, if this is 4, and that's 1/3 of the whole thing, very good. All you have to do is double it to go the other way. That means this is 8. Because what's 8 plus 4? 12. Yes, ma'am. Median. Sorry, it was median. It seems really, really weird to see fractional parts for this kind of stuff. But as you get into it, think about the segments. 2/3 the median is vertex to centroid. 1/3 of it is the centroid side. Okay. It sounds really, really, really weird, but if you realize that 2/3 is just double 1/3, 1/3 is just half of 2/3. So don't freak when you see this whole idea of the fractional amount. It is very, very easy to work with. Okay? Same thing goes for, if I say that this chunk here is 12. That 12, is that segment the whole median? Is it vertex to centroid, or is it centroid to side? So that means it's 2/3 of the whole thing, correct? So the other part of it would just be half of it. What's half of 12? 6. See how easy that is? It doesn't necessarily have to worry about the 2/3, 1/3. Okay? You can do, I can say that this whole thing here, this entire median, the median, we'll call it A, call this guy B, C. I can say that AC is 30. If the entire thing is 30, what does that make up to be the small chunk? Very good. If that means that the small chunk has to be 1/3 of 30. When you take a third of something, all you're doing is taking that number and dividing it by 3. You guys knew that, right? So don't frequently see the fraction amount. So if the one part's 10, what's the other part have to be? 20. All right? It works clean. You're not going to, even though I know you guys are probably thinking, oh man, when I see 1/3 and 2/3, and you can see all these decimals repeating all over the place. It doesn't happen that way. A lot of times the numbers become super clean with this because they know that math sucks and they don't want to overbearing you guys with some of these things. It's the idea that you can write out what part are you working. I mean, yeah, I can't think of anything. I mean,
even when we do algebraic expressions, they do it. Boy, you guys have that calculator that you're supposed to have in this class? Because if you do, it'll make this next part like when you have to do fractions with an expression.
It's just use the fraction bar on it and you hit a couple of buttons.
Or you can use the next one.
All right, let me show you what happens here. For example, now again, don't draw all this out. It tells you that A is the centroid. Okay, A is the centroid, and then it says that XA is 8. Is that vertex to centroid, or is that centroid to side? It's vertex to centroid. So vertex to centroid has to be the larger of the two. What's the other side? 4. See how fast that is? It looks like it's going to be awful with those fractions, but in essence, it's really, really quick. It's the idea of what part do you have? Okay? Not terrible? Altitudes. Excuse me. Altitudes are a little weird. You guys have all had your moms and dads yell at you, stand up straight. Stand up straight. Because when you stand up straight, that's as tall as you're going to be. I'm telling you, there's going to be two things I'm going to invest in. I'm going to invest in back braces and miracle ear. You know what a miracle ear is? Hearing aids. You know why? You guys are all going to be deaf by the time you're 30. Seriously. No, I'm not wrong. I'm not wrong. It's a strong investment. It's pretty good. It's good. I got like $20, I think. I think what are you doing now? Yeah, I got $20. Well, we'll do some day trading next hour. So an altitude is the segment that's perpendicular from a vertex to a side. So altitudes are weird. You guys have actually worked with these before. And you've seen them both inside triangles and outside of triangles. We normally call the altitude the height of a triangle. Because whenever you measure anything, you're always measuring the heights where things are perpendicular. So if I wanted to measure the height of this, I'd have to draw this to become perpendicular to that side. That would give me the height and what a base would be of the triangle. It's weird because you haven't seen it in a while. You've also seen it like this. Sometimes, remember when you guys had triangles, you had to find area? Sometimes they would draw like that. This is still an altitude of the triangle. It's just drawing it outside of it. It can happen. When you have, excuse me, when you have what are called obtuse triangles, you can have altitudes drawn outside of it. And that's perfectly fine. You guys have all seen that before, but you just didn't know that they were called altitudes. They were just usually called for you guys the heights. Am I right on that? So what happens here is that the altitude of the triangle can be inside or outside the triangle. It can be, or it can be the actual side of a triangle. What happens when it's the side of a triangle? When you have a right triangle, because it's basically drawn from a vertex perpendicular to the side opposite. Okay. So it can be in a couple of different places. When you deal with them, I think for the most part, when we look at them, I don't really wind up being inside. They don't try to mess it up too much. But it goes from there. But you guys have all seen them before, right? It's just, you guys were just all, they were just taught it to you guys before as they were the heights of the triangle. We're just going to change the name. So what happens here is that the altitudes, the three altitudes, are concurrent, excuse me. Yeah. The three altitudes of a triangle are also what they call concurrent, which means they're going to run into each other. Which means they also have another weird name. Let's see if I can draw it here. Good luck, thanks. If you want. The point at which the three altitudes hit, the point at which all three altitudes hit, I believe they call it, I think this textbook calls it the ortho center. Can I go to that screen? I'll redraw this picture here in a second, guys. The point at which they call it is called the ortho center. Well, let's just worry about what it looks like on an acute triangle right now. The ortho center is where the three altitudes hit. Can I use ALT for altitude? You okay with that if I use that abbreviation? It's where the three altitudes intersect. Like they were saying, you could have, it can be inside, outside, or on the circle. I think more often than not, we try to make sure you guys see it. We try to put them, no problem. We try to put them inside the circle, or it's actually circle, I'm sorry, inside the triangle, or on the triangle. It tends to be a little bit weird when we put them outside the triangle with the obtuse ones, because then you got a bunch of imaginary lines you got to worry about. I'm running out of words. That's why I had to put this morning. What's that? And if you think about it, when you're looking at a right triangle, it's really easy to find it. The orthocenter for a right triangle is always going to be at the right angle because two of them meet right there, and the third one gets drawn from there. So in a right triangle, it's always going to be at the right angle, but the ortho center is a little bit different. I'm sorry, what? Yeah, if it's on a right triangle, if you're on a right triangle, if you think about what happens here, and remember, an altitude is the segment drawn from the vertex to where it's perpendicular. Well, in order to create a right angle, you are perpendicular at where two lines intersect. Those two lines came from vertices. So we know that they intersect here, and then the third one, it starts here and works its way out. So the orthocenter is at that right angle. That comes into more into play into second semester. We actually don't teach it all that often anymore about what are called similar right triangles, because that's the basis of that, of why certain other things happen as far as ratios of Pythagorean theorem and all that stuff. Yes, ma'am. No. Sure. Come on now. It's like December. You haven't figured out the sarcasm yet? So, excuse me. Ugh. I don't wish this cough on you guys. This is bad. Good. So basically, the orthocenter does. I don't believe it's going to worry about any of the fanciness. We'll come back to this one tomorrow when we draw out our big thing. But what I want to do is just kind of show you guys a couple of examples of what we can do with these. Yep. Okay. G is the centroid. G is the centroid. Let's find all these other segment lengths. G is the centroid. Let me blow this up so you can see it better. So when you deal with the algebra, this is where things can get a little bit weird. For example, if I start this problem out here, it says G is a centroid of ABC. G is a centroid of ABC, and we're first going to look at the problem about CG and CD. What I was going to make a quick suggestion here. What were you going to say, Josh? Exactly. You're just a step ahead, which is fine. Now, when you have a problem like this, you've got a whole bunch of different segments and stuff like that. Take a second and look at the diagram before you draw the whole thing and know that you're looking at just that portion. So what I would do is just take that portion and label. Well, I know I have E, G, and C. This part was the 3x plus 7. This part's the 6x. And like Josh just said, since G is that centroid, I know that 2/3 of it is here, 1/3 of it is here. Which means, if you think about it again in terms of numbers, just for old time's sake, if this is 10, this has to be what? 5. So how would you set those two equal to each other? What would you have to do to this to make it equal to that? Times it by 2, exactly. So when you're dealing with these things, one of the other little notes you can put on for this, if you double the centroid to side, it equals the vertex to centroid. That's a nice little thing to make sure you have. Okay. So just like Josh said, 2 times the 6x has to equal 3x plus 7. That was 7, wasn't it? Yeah. So what's 2 times 6x? 12x. Subtract 3, and x equals 7/9. Just like we said before, guys, it's okay to get fractions. FG and AF. Well, FG is the small portion, AF is the whole thing. Which means FG is 1/3 the size of AF. Okay with that? Write this out.